In this video, I will go over your Unit 8 Calculus review over differential equations. So the first one here is a slope field problem, and we're supposed to match this equation to one of these slope fields. One thing I always look for is what is going to create a zero slope. So in this case, if x and y are the same but opposite, our slope is going to be 0. So here we're looking for this diagonal to be 0 slopes, which doesn't happen here, doesn't happen here. Here, the positive, when they're the same, they're 0. Here, when they're the same, they're 0. And when x is greater, we have positive, or if we had a positive, positive, we get positive, negative, negative, we get negative, and so on. So this one is our answer. The next one, which corresponds to the different equations? Well, if I look here, all my slopes in this quadrant are negative. All my slopes in this are positive. These are negative. These are positive. Okay, so looking at these, this one would be negative in the first quadrant, but it would be positive in this quadrant. No. 0 slopes. Look at that one. Here, when x is 0, my slopes are 0. When my y is 0, it's vertical. So we're looking at the numerator being 0, the numerator being x, the denominator being y, because that'll give me those 0 slopes and undefined slopes. And then if the first quadrant and third quadrant are negative, our function is going to be negative. So it is not that one. This next one, if we look at the solutions to these, if I were to solve this differential equation, we'd get 200t plus c, which is linear growth. This one, if I solved it, it would just be quadratic. So it would be 200 times 1/2 t squared. If I solved this one's going to be cubic. It'd be 100 times 1/3 t cubed plus c, which is going to be cubic. This one, when we solve it, when we have my separation of variables, we get tp over p equals 200 dt. This is our general solution for an exponential. When I solve this, we're going to have p equals ce to the kt, or 200t, which is exponential. In this next section, we are just solving the general differential equations. So we separate, integrate, and solve for y if necessary. So if I separate here, we're going to have dy equals 2 dx, then integrate. Y is going to equal 2x plus c. These two, and these are purposely written next to each other, 2x versus 2y. Well, 2x, when I separate my variables, we're going to have dy equals 2x dx. If I integrate, we're going to have y equals x squared plus c. Compared to this one, when I separate the variables, we'll have dy over y equals 2 dx. So now when I integrate, we're going to have the natural log of y equals 2x plus c. Or you could recognize that this is going to be exponential. So we'll raise both sides to the e, and we get y equals ce to the 2x. Next two, again, same kind of structure, but x versus y. So dy equals x cubed dx. Integrate that. Y is going to equal 1/4 x to the 4th plus c. This one, we're going to have dy over y cubed equals dx. I'm going to rewrite this as y to the -3 because it makes the power rule a little bit more obvious. So I'm going to add 1 to the power, which is going to make it to the -2, then multiply by -1/2 for the chain rule. Then on this side, I'm going to have x plus c. Now we want to solve for y here. So I'll multiply by -2. Okay, this is going to be the same as 1 over y squared equals -2x plus c, which means y squared is going to equal 1 over -2x plus c. And then I'll take the square root. So this is going to be square root of 1 is 1 over plus or minus the square root of -2x plus c. Next one, to get my variables together, we can just simply cross multiply. Then if I integrate this, integral of 1 is y. Integral of y cubed is 1/4 y to the 4th equals x cubed plus c. With a y to the 4th and a y to the 1st, I'm not going to be able to solve for y. So we're done with this one. All right, x over y versus y over x. Well, if I have x over y, that gives me x dx equals y dy. So 1/2 x squared plus c, I did that backwards, sorry, equals 1/2 y squared plus c. No, plus c. Multiply both sides by 2. And then square root. So this is going to be plus or minus the square root of x squared plus c. Or you could write it with the conic section, which would be x squared minus y squared equals c. Here, dy over y equals dx over x. So ln y equals ln x plus c. Okay, if I raise both sides to the e, this is going to be c e to the ln x. Well, e to the natural log of x is just x. And since c could be plus or minus, I can just write this as cx for my final answer. Okay, this next one, separate 3, I'll write this as x to the 1/2 dx. Then integrate. So this will be y equals 3 times, if I add 1, I'll have 3 halves. So I want to multiply by 2/3 plus c. So if we want to clean that up, we have 2x to the 3 halves plus c. Okay, our next one here, I'm going to leave the 3 but divide over the square root of y. Okay, I'm going to integrate. What I'm going to do though is I'm going to sneak a 2 in here, but if I do that, that's the same as multiplying by 1/2. I'm going to put a 2 on the outside because we know that the integral of this is the square root. So this is going to be 2 root y equals 3x plus c. Divide by 2. And then square both sides. So now we're going to be solving a differential equation, and we're going to find the particular solution. So we're going to find the c. So first thing I would do here is add the x cubed and y squared to that side of the equation. Now I can separate. So dy over y squared equals x cubed dx. And then we can integrate. Okay, well we know the derivative of 1 over x is negative 1 over x squared. So the integral of this is negative 1 over y. equals 1/4 x to the 4th plus c. I'm going to go ahead and solve for my initial condition here because my condition is y of 0 equals 2. So negative 1 over 2 is going to equal, this whole piece is going to be 0 plus c. So my c at this point is negative 1/2. So then I'll continue solving with that. So negative 1 over y equals 1/4 x to the 4th minus 1/2. Okay, I'm going to do a little work on this side. I'm going to get a common denominator. So I'm going to make this x to the 4th. If I get a common denominator, this would be 2/4. So x to the 4th minus 2 over 4. Okay. So then I'm going to flip it and make it the opposite. And you can have different solutions that look like this, but the negative, I can move that over, and then we just flip the fraction. But you must have a whole fraction before you flip it. You can't just flip it at this point. Okay, in part B, using your solution from part A, what is the value of y of 1? So I'm going to plug 1 into my newfound equation. So we're going to have negative 4 over negative 1, which is going to be a positive 4. Okay, now we're going to find the particular solution if y of 2 is 4. So up to this point, we have the same thing. Okay, I don't have to start from the beginning. I just need to plug in this into here or later on, but I'll just do it now. So negative 1 over 4 equals 1/4 times 2 to the 4th plus c. So negative 1/4 equals 16/4 plus c. So my c is going to be negative 17/4. Okay. Then I'll plug that back into negative 1 over y equals x to the 4th minus 17/4 with our newfound c. So negative 1 over y equals x to the 4th minus 17 over 4. So y will be negative 4 over x to the 4th minus 17. Okay, the slope of a curve is 8x over y. If the curve contains the point 1, 1, find the equation of the curve. So another way of saying this, slope is dy dx. So we're saying dy dx equals 8x over y. So then we separate. Then we integrate. We can plug in our initial condition at different points. I'm going to go ahead and take this a little bit further before I do. So multiply both sides by 2. And then I'm going to take the square root. Okay, so for this one, for the initial condition, if I'm plugging in a 1 and getting out a 1, that means here we want the positive version of this. Had we had the point like 1, negative 1, then we'd have the negative version. So this is going to be y equals positive 8x squared plus c, and then we'll plug in 1. So if I square both sides, 1 equals 8 plus c, so c is negative 7. So my final equation will be positive square root 8x squared minus 7. So for our next problem, Newton's law of cooling states that the rate of change of temperature of two bodies in contact is proportional to the difference in their temperatures. The temperature of a house is 70 degrees now, and the outside temperature is 35 degrees. If the furnace is turned off, so the house is going to cool down without any added heat. The differential equation for that is dt is 3/4 35 minus t, where t, little t, is measured in hours, and big T is the house temperature. So we're going to write the equation of the line. a tangent line to the graph of t at t equals 0 and use this to see what the temperature is going to be in 1 hour. Well, if we want the slope, or if we want a tangent line, we need a point and a slope. So at t equals 0, our temperature is going to be 70. So this is a little bit different. Our x's are big little t, our y's are big T. The slope, though, is going to depend on just what big T is. So dt at t equals 70 is going to be 3/4 35 minus 70, which when you do this and you'll have a calculator is negative 26.25. So now that I have a point and a slope, t minus 70 is going to equal negative 26.25. Little t minus, what was our 0? So t equals negative 26.25 little t plus 70. Well, if I plug in 1 into that, we're going to have 70 plus this is 6.25 times 1. Gives us a value of 43.75 degrees. So we're going to go with, there's not some good insulation on this house if your house goes from 70 to 43 in an hour. But that is our prediction based on the tangent line. In part B, we're going to use that prediction, or we're going to use a second derivative to determine if this is an overestimate or an underestimate. So I'm going to take the second derivative. So dt, I'm going to distribute the 3/4 to make my life a little easier. Okay, because then if I take this derivative, d2t over dt2, derivative of this is 0, so we're going to have minus 3/4, but we're taking the derivative of t with respect to little t. Okay, then I'm going to go ahead and replace this, because that's why we want to determine t2 equals negative 3/4 times 3/4, 35 minus t. So that would be negative 9/16 times 35 minus t. Well, what we're going to use the fact, what does second derivative tell us? It tells us about concavity. So we want to figure out if it is concave up or concave down. Well, our second derivative here will be 0 when the temperature is 0. If I plug in a number less than 35, we get a negative value. If I plug in a number bigger, this will be negative, this will be negative, so this will be positive. Now, if we think about this situation, though, the highest this graph is ever going to be is 70. The lowest is 35. It's not going to go, temperature of the house isn't going to go lower than the surrounding temperature. So for the entirety of our range, in this case, our graph is concave up. And if we have a tangent line where our graph is concave up, we're going to have an underestimate. Concave up, because the second derivative is positive. Okay, for logistic population growth, the rate of change of the population is low when the population is small, reaches a maximum for moderate population, then gets lower again as the population becomes very large. In this case, dy dx can be a quadratic function of y. Anyway, suppose this is our differential equation. Show that the population is increasing if y is 1 and decreasing when y is 10. So dy dx evaluated at y equals 1 is going to give me 0.05 times 1 times 7 minus 1. So we're going to have a positive 6 times positive, which is greater than 0, so it's increasing. if I do the same thing at y equals 10, then we have 0.05 times 10 times 7 minus 10. So we have positive, positive, negative. So it is decreasing. Okay, on the slope field below, sketch the graphs of the particular solutions for when y is 1 and for y is 10 and x is 0. So here, when y is 1, we're starting at this pot, and you're just matching the slopes at the point. Your graph should run parallel to what's happening. Okay, and then it levels off here. If we do this at 10, we're up here. We've already established it's going to be decreasing there. Okay, so we're just following it. The main difference, this one's always decreasing, this one's always increasing, and they're both going to a leveling off spot. Okay. Show algebraically that the population is stable at 7. Well, if I plug in 7, then we have 0.05 times 7 minus 7. Well, that's 0. And then if we show this on the graph, if I draw a line starting at 7, straight across there. All right. On this one, we're going to graph the slope field for 2xy. So when x is 0, my slopes are 0. When y is 0, my slopes are 0. Okay, so then I have 6 I need to calculate. 1 times 1 is 1. 1 times, sorry, it should be 2. 1 times 1 times 2 is 2. 1 times 2 is, so that's going to be 4, pretty steep, and this one's going to be real steep. Okay, these will be negative, positive. So 2 times negative 1 times 1 is a negative 2. So I'll just kind of aim right through the middle. Negative 4, and then negative 6. Okay, while the slope field in part A is drawn for only 12 points, it is identified at every point in the xy plane. Describe all the points in the xy plane for which the slopes are positive. Well, in order to get a positive number here, we're multiplying two numbers. So if x and y are positive, we'll have positive. If x and y are both negative, we'll have positive. So in quadrant, oh, we want negative, sorry. So in quadrant 2 and quadrant 4, if I have a positive negative or a negative positive, we will have a negative slope. All right, next we have Euler's method. So we're going to let y equal the particular solution with the initial condition f of 0 equals 1. Use Euler's method, starting at x equals 0 with a step size of 0.1 to approximate 0.2. Show all of your work. So first we'll draw our chart. Okay, so our columns are x, y, or you can just do the point together if you prefer. I'm going to calculate dy dx. So we're starting, then once we have the slope, we'll multiply by the delta, so how far we're going. Then we'll add our new x and our new change in y. So our starting point is 0, 1. So if I do 2 times 0 times 1, I get 0. 0 times my delta of 0.1 is 0. My new x is going to be 0.1. My new y is still going to be at 1 if we have a slope of 0. So we're going to have 2 times 0.1 times 1. So this will be 0.2. 0.2 times 0.1 is 0.02. So at 0.2, my point is approximately 1.02. Okay, now we're going to find the particular solution and compare it to the actual f of 0.2. Okay, so for our particular solution, we're going to separate our variables. then integrate. So y is ce to the x squared. We'll plug in our initial condition where 1 is equal to ce to the 0. So c is 1. So that's e to the x squared. Now we'll use our calculator, plug in 0.2 into our equation, and you get 1.041, which is pretty close to our 1.02. Our last problem here is a logistic problem. So you just need to understand the structure and the general solution. So we're going to find K and the carrying capacity. So when it's in this structure, K is going to be 0.06. My carrying capacity, which we'll call M, is 800. Okay, so with that, we're going to find the formula. So P equals, my carrying capacity is 800 over 1 plus AE to the negative 0.06 T. Okay, you do not have to solve this generally. You should know this formula. We're going to solve for A. So 25 equals 800 over 1 plus, if we plug in 0, we're just going to have A. So 25 plus 25A equals 800. So A is going to equal 800 minus 25 divided by 25, which is 31. So my general solution here is 800 on top over 1 plus 31 e to the negative 0.06 t. Okay, if we plug in, so if P of 0 is 25, for what value of P is the population growing the fastest? This information does not affect the answer. Okay, the population is growing the fastest at the point of inflection, which is always going to be the carrying capacity divided by 2. That's where that switch in from increasing exponentially to slowing down is going to occur. How long will it take for the mountain lion population to reach 450? So we're going to use the calculator for this. All right, so I've typed 450 into one of my y equals, and I've typed in my equation into the second one. The window's going to be the important part here. So for my x-axis, that's time, so we don't care about negative time, and I don't know how long it's going to go. So let's do like 50 years. If we need to adjust, we will. For the y's, we need to at least see 450. So I'm going to go from like let's just do 400 and 500. That'll put 450 right in the middle there. Or we could look at more. How about just go from 0 so we can see the logistic curve. Okay, so there's my goal is 450. Here's my logistic curve. It's exponential, growing, growing, growing. And we haven't reached it in this time. So I'm going to make let's go to maybe 100. And we're almost there. Winner. So then we'll go to second calc, intersection, enter, enter, enter. And our answer is 61.4 years, since we're asked to round to the nearest 10th. So 61.4 years. So that is your Unit 8 Calculus review. Good luck.